All right. Hello, everyone. My name is José Pedro Ferreira. I am an aerospace engineer, and I'm also a PhD candidate at the University of Southern California. As we're going to take a look into this thin layer that essentially protects us from the harsh environment outside our pale blue dot, I'm going to invite you to take a deep dive into how humankind affects or interacts with our atmosphere, essentially by doing activities in space. And let me tell you, just to start off, that this is by no means a new concern. But let's first perhaps recap the overall life cycle of essentially placing an asset in orbit. Firstly, we put it at the top of a rocket, then we launch it into space, release it at its nominal altitude, it fulfills its mission, and then hopefully by the end of life, it will come down to the atmosphere and end its life in a fiery demise. If we think at the first step of this journey, and if we think of the impacts that it may have in the atmosphere, the launch stage, we can think of this exhaust plume of the rocket essentially injecting substances across different layers of the atmosphere. This was something that essentially back in the 90s concerned some people, but we were fortunate to essentially rule that out by studying how this plume interacts with the atmosphere. And in this case, and at the launch cadence in the 90s, the space shuttle played a very decisive role in bringing clarity to this and saying that at the moment there is no problem with regards to this. However, with the increase of launch rates at the moment, also with the change for other types of fuel, especially on the liquid spectrum, there is a resurgence now on this type of questions. And also people start wondering about the impacts of re-entry in the atmosphere. And in this latter case, we may think of spacecraft and upper stages of launch vehicles that essentially at the end of life will just end up in the fiery demise in the atmosphere. This happens essentially because of the huge velocity that these objects carry while encountering a denser atmosphere as they come down. Essentially, this means that there is an increase in temperature on the surface, and essentially, kaboom, there is a fireball essentially throughout the layer of 60 to 90 kilometers of altitude. And this is only a concern because of what I amicably call this mass imbalance between what leaves Earth and what stays in orbit and comes back down afterwards. So since 1957, we started reducing ever so slightly the mass of our planet by putting anthropogenic objects in orbit. This, of course, we are currently at the deficit because we keep on adding more and more mass than what comes down. And there is also a time component to this, because if we think about the launch and re-entry cadence, there is a delay between these two events. This is essentially associated with the mission duration and the residual orbital lifetime. And essentially the result of it is congestion. This is our classical orbital debris problem that threatens a sustainable access to space in the long term. We also shortly after came to realize that the only feasible solution, at least for the time being, is bringing all this stuff down to clear the orbital environment. So then we come to ask ourselves whether this is actually significant. How does it actually compare with natural sources such as micrometeoroids, interplanetary dust? Are we actually talking about the case of a drop in the ocean? Is this actually significant? So we know that meteoritic smoke is likely assumed to play a role in the processes in the stratosphere and the mesosphere. And we think that spacecraft may have similar impacts on it. But we don't know to what extent yet. What you see here, you probably may have guessed that this is a beautiful meteor shower, but it's not. This is essentially the end of life of a spacecraft. This is how a spacecraft demise at the re-entry in the atmosphere. So what we look into here is essentially the chemical composition of both, and we try to compare both sources. How do the actual chemical composition of spacecraft, especially the atmospheric uptake of these chemical species, compare between human-made and natural sources? And we may think of metallic alloys that are essentially the backbone of spacecraft structures that include chemical species such as aluminum, titanium, copper, even lithium from the batteries, and see how it compares. So to understand a little bit better this, I invite you to zoom in into these tiny little chunks that are generated to further understand what is actually happening. So during this very hot stage of reentry, essentially most of the mass burns. And we are happy that it does, because this is essentially what prevents all these mass to come to the ground and hit us. So this is good. This is exactly what we want. The thing is, we don't have a very good grasp of how things break up. We just got really better at estimating the probabilities of what actually makes it to the ground. And we are actually pretty good in protecting humans, or in making sure that nothing falls in our heads. So as we can see here, part of the mass that re-enters fully vaporizes. Another fraction will essentially become these bits and pieces that we see here, and hopefully a very small fraction survives re-entry. So as we see, there are different shapes and sizes for these bits and pieces. And this is exactly what we are interested in, because essentially size here matters, and it will dictate how long will these particles reside in the atmosphere. And essentially, this is the backbone, the core driver to understand the future environmental impacts. So here I invite you once again to take a look at what's left from the re-entry event. And then we zoom in into these even ever so slightly tiny little pieces to understand what happens at the atomic level. And here we do what we do best with limited resources. We model it. So here we are looking into essentially, let's imagine that we are scooping into the structure of a spacecraft that is re-entering the atmosphere at very high temperatures. And then it faces the increasingly denser atmosphere. This is already in molten state, as we saw before, and the result is particles, or are ever so slightly smaller particles, I should say. What this essentially tells us is that there may be even smaller particles than what we saw in the previous image. And as I mentioned earlier, the particle size is the driver. So what we wonder is, what is the sensitivity of the atmosphere to this different particle size, and how long will these reside in the atmosphere? So then we use this as input for atmospheric models. And essentially what we see here is a timeline for the trajectory of different particle sizes, in this case of aluminum oxides, injected in the atmosphere. This injection usually takes place in the mesosphere. In this specific case, we are talking about injection between a latitude of 40 and 80 degrees north and south. This is for a pattern of uncontrolled re-entry. And what we see here, firstly, is, we know that these particles will be conducted to the poles. We know that they are pushed down during the winter season. And we are seeing here what we kind of expected. So larger particles will settle faster than smaller ones. But what I want to bring your attention here to is to the sensitivity of it. So larger particles will settle in about 1 year to stratospheric altitudes close to the ozone layer, whereas 10 times smaller particles will take more than twice as long. And this is an interesting take, because it tells us that 1 order of magnitude in these particles would essentially have a significant impact in the atmospheric residence time. But now I would dare to say that this is just part of the equation. I would invite you now to take a step back and look once again at the infrastructure that is used to bring these assets into orbit, launchers. Let's look now at launch emissions. How would a 10x increase in launch cadence from Cape Canaveral look like in 2100? So this is a very thought experiment. And in this animation, what we see is a sweep from the ground to a 30 kilometers altitude of a scenario of increased launch cadence from the Cape Canaveral. This is essentially a scenario that is compared with a baseline for the same time span. And what we see here is that this tiny little red spot will persist in Florida across the vertical column of the atmosphere. We see that it will start migrating west due to winds, and essentially the concentrations will start peaking at the poles and then coming down to the equatorial latitudes. So all these are hypothetical scenarios, and it clearly shows us that we don't know a lot about this, but it also indicates that there is a reason that we should be curious about it. So this is essentially what tells me that there is a long road ahead of breakthroughs and discoveries to unveil the mysteries of the generation of these tiny little particles, which essentially are based on resolving the uncertainties that are the backbone of these microphysics and chemistry processes. But the good news is that, to my opinion, we already have the instruments and facilities to essentially proceed in these quests for resolving these uncertainties. Firstly, we can think of our beloved WB57 with those nose imagers that essentially during a controlled reentry event can point upwards and resolve either the particle size distribution or the chemical byproducts from these reentry events. We can also think of using the same platform in stratospheric altitudes to collect pieces of data that could probe for the existence of exotic space metals in the stratosphere. This was already attempted, done, but not in different regions of the globe. On the other side, we can think of using our state-of-the-art plasma wind tunnels to essentially generate data to compare with the first one, and then ultimately answer the question of what's the mass fraction that is actually vaporized and how it will interact with the atmosphere. And then all these data can be used into atmospheric models to provide a more concrete long-term estimate of the impacts and interactions with the atmosphere. So looking at the historical data and to forecasts, the future is at least worth investigating. There are clearly a lot of uncertainties here, especially with the degree of completion to these large projects for in-orbit infrastructure that include, but that are not limited to, constellations of spacecraft. Then afterwards, and using this knowledge on how to resolve these byproducts of launch and reentry, we can then put better estimates of how these will interact with the atmosphere. I should point out that preliminary research already suggests that there may be some potential impacts in radiative forcing, in stratospheric ozone concentrations, and in the nucleation of high-altitude clouds. So I want to conclude this little conversation with you guys by suggesting that whether human-made starry night over the Mississippi or, as initially depicted by Van Gogh, over the road matters to you, I feel that this quest for answers to these questions will persist. In the meantime, we hope that we can see the lights from stars clearly and that we can keep breathing just fine. Thank you.